Hey guys, hello, welcome to this video. Today we want to present the solutions or the editorial for the contest Codeforces Round 799, which was a Div 4 contest. So since this is a Div 4 contest, I want to congratulate all of you who decided that this would be the contest that you would start, and I hope that you have a great competitive programming journey ahead. So without further ado, let's go into the solutions. Okay, so problem A is marathon. So we have been given four distinct integers a, b, c, d, where let's say a is the speed that we run at or Timur runs at, and b, c, d are the other participants. We want to find the number of participants in front of Timur. So the number of participants in front of Timur would be the ones who have a higher speed than Timur. So we just input Timur's speed and other three speeds, and individually we go through all of the speeds one by one, and if the speed is greater than a, that person will be ahead of Timur. So we increment 1 to the answer. We initially have answer is equal to 0. If we get b greater than a or c greater than a or d greater than a, we understand that this person runs faster than Timur. Thus we increment the answer, and thus at the end we just increment the final answer, which is the total number of people ahead of Timur. Let me just check if everything is fine. Yeah, everything is cool. Okay, so I hope this solution was clear enough, and let's move on to problem B. Okay, so problem B is an interesting problem. We have been given an array which contains some duplicate elements and some elements which are not duplicate. So for example, we have 2, 3, 4, 2, 5. Here 2 is appearing 2 times, but other elements just occur like 1 time. What we want to do is we want to remove all duplicate elements, and at the end we just want to have all unique elements. And the way we can remove elements is that we can choose any two elements and remove them. So first we want to find how many elements we actually have to remove. So we just add all of our elements to a map. So for example, if number 2 is appearing 4 times, so m of 2 in the map should be equal to 4. That's how we are going to store it. So at the end, when we see that m of 2 is equal to 4, we know that we have 3 duplicates which we have to remove. Thus we iterate over the map, and map works in such a way that I dot f is the key and I dot s is the value, where I is the entry in the map. I is the key value pair in the map. So if we have I dot s greater than 1, that means that the element has duplicates. We add the number of duplicates. So one of the copies is original, which we can keep. Rest all we have to delete. So the number of copies we have to delete is I dot s minus 1. So we add them to the answer and we get our final answer. Now note that if my final answer is say something like 15, I cannot choose two elements 7.5 times and remove these 15 elements. So I would have to waste half of a turn, and I would require 8 turns to remove these 15 elements. So for the first 7 elements I will remove 2 which I actually want to remove, and for the last turn I will just remove one particular element which we need not remove, but we just removed because we had to complete the turn. So if my number is not divisible by 2, I have to remove one element which I would not want to remove. So these are all the elements which we've had to remove, which I have marked by answer, and we have to tell what are the final length of the array. So basically all the elements which are not removed will be left, so that number would be n minus answer. That should be the solution of problem B. I hope it's clear. Let's move on to problem C. Okay. So problem C is, you have been given a chessboard, which is always an 8 by 8 chessboard, in this question at least, and we have a bishop. We can keep it at any particular place. So you know how a bishop works, right? It attacks all of the elements in a diagonal. So if I place my bishop in the 4th row and 3rd column, it will attack all of the squares colored in red, which are the diagonal squares. So we have been given a diagonal structure as to which squares are being attacked, and from that we need to find where the bishop is actually being placed. So initially I was thinking of considering slopes and stuff, but I realized that the constraints are very small. They are just like r comma c from 2 to 7. So what we can do is we can have a r to the power 4 solution in which we go through every possible place where we can have a bishop. That will those are r times c place, those are 8 times 8 number of spots, those are 64 spots, and from each of the spot we can check all of the 64 squares once again if they are correctly marked as they can be targeted, or they are wrongly marked as. If any square is wrongly marked, then we know that the bishop cannot be placed here. So this is a very straightforward brute force r square c square complexity. Sorry, n to the power 4 complexity solution where n is the number of rows and columns in the grid. So I just input a grid. I'm using a macro. You could just input it one by one. So what I want to do is in the first two loops I iterate through all of the position in which I can keep a diagonal a bishop on. Then once I get the place, so basically if I'm running this loop, I know that my bishop is going to be placed at ith row and jth column. So from that we want to check if the given grid structure that we have given makes sense for this particular position. So what we want to do basically is that uh, a bishop will attack both diagonals. So let's move here. I'll show this. I'll just try to show this. I'll try to demonstrate. So for example, let's say I have a simple 4 by 4 and I keep a bishop here. So how do we know which square is actually bishop attack? So visually we can say that these are diagonals, but we need some mathematical representation to understand where they would actually attack. So how it turns out to be is, let's say my bishop is at position I comma j. Then one thing you can realize is that this is a straight line and this is a straight line. So this straight line has a slope of -1 and this straight line has a slope of +1. So what it turns out that every point on this line has the same j minus I as our point. So if our point has a j minus I value of 4, all of the points on this line will have a j minus I value of 4. So we will look through all of the points, and if any of these points have j minus I value equal to 4, we can understand that these points are on this primary diagonal for this bishop, and thus the bishop can attack them, or the bishop must attack them. Similarly, if you want to look at this diagonal, the anti-parallel diagonal, you can understand that all of the points have a similar I plus j as our original point. So if when traversing through all of the points, if we find out that our I plus j value is equal to the actual I plus j value of our bishop, then this position must be targeted. That's how I'm going about it. So I define these two diagonals. One diagonal is defined by j minus I and another is defined by j plus I. Then again I have a loop which travels through all of the rows and columns and checks each individual grid point if it is correctly assigned. So if L minus k value is equal to diagonal 1 or L plus k value is equal to diagonal 2, that means that it is one of these points, because they either lie on the primary diagonal or anti-primary diagonal of the bishop. And if it is so, then we cannot have the grid value to be equal to a dot. It has to be equal to a hash, because this point is necessarily being attacked. So if it is so, I say that I say OK is equal to false, which means that this point can never be a point where the bishop is placed. Similarly, if it is not so, we know that bishop can never attack such a point. And if it still attacks such a point, if it is not equal to an empty, not equal to just a full stop, then even then OK should be false, because here we had to have grid value to be equal to a full stop, because the bishop cannot attack a point which does not lie either on the primary or the anti-primary diagonal. Now if our answer is still okay after iterating to all the points, this means that it is the correct spot for the bishop, and we just print it. Since while taking a grid I just use 0 indexing, while outputting I should use 1 indexing, so I do so I print I plus 1 comma j plus 1. That is the solution. This was an interesting problem. I'm not sure if I think there are solutions which will be with a much lower time complexity. Those are interesting ideas. I think we could think about them. So let's move to D. Okay. So generally in such a problem when I have clocks, I don't find it good to use all of these hours and minutes notations, because it's not decimal and it's kind of confusing. So in general, what I do is always just convert it to minutes and then deal with it. So that's what I do. I input the string and the number first. Now I want to find out what 3 hours and 12 minutes means. So I will just multiply 3 times 60 plus 12. So that is 192 minutes. So how do we do that? We look at the first position in the string, which is this position. This means 10 hours, which is 600 minutes. So if this bit is 1, so if this index shows 1, I have to multiply it by 600, because it is 10 hours, which is 600 minutes. Similarly, the second position over here, okay, let me just zoom in, which is this position 3. It is basically 60 minutes. So SI minus 0 times 60. Then I have to skip one position for the colon. So don't write S2, you have to write S3 because S2 is the colon, which will not give you anything. This position is worth 10 minutes and the last position is worth 1 minute. So this is how I convert from a completely hour based system to a minute based system. But you might ask, we have to check palindromes and stuff. For that we might need to go back into the hour situation. That is fine. I find it much easier to convert to minutes and then increment the minutes and then convert back to hours. I find that's a better way to go through it. So that's how my solution works. So let's go through it. And yeah, so this is the minutes that the clock is at right now. And what I want to do is I also want to stop when I complete 24 hours. Uh, so when I come back to my original position, I want to stop because you are not going to get any more palindromes after that point. Just a second. Yeah, you're not going to get any more palindromes because you've already iterated through all the possible numbers. There's nothing more that's going to happen if you go through it another time. So I just store it as the point where we started from, and if we reach back to that point, I'll just stop it. So now I first check if the given time itself is a palindrome. If it is, I'll plus the answer, and after every checking, I'll just increment by x because what they say is that after every x minutes you will check once again. So I have to continue incrementing by x, and suppose it crosses the whole 24 hours. So if time is like 11:59 p.m., which is 23:59, and you check every 5 minutes, so next time you would be checking at 0004. So you also have to mod by one whole day, which is 1440 minutes. So which is 24 hours into 60 minutes. So if it crosses that, I'm just going to mod over that. That's what I'm doing. Now similarly, I just continue the while loop till I get back to the same position, and every time I get a palindrome, I increment the answer and print the answer. Now the interesting part is how do I find the palindrome. So for that I have defined a function so it looks clean and nice. So what we want to do, look at this number 312. So what you wanted to do was match 0 to the 2 and 3 to the 1. So the tens place in the hour should match the units place in the minute, and the units place in the hour should match the tens place in the minute. So that's how we do it. So empty mod 10 is the uh, units place in the minutes, because empty is the total number of minutes and you just mod it by 10. So anything which is higher than 10 minutes is the belongs to some other digit place. So empty mod 10 is the very last digit over here. This should be equal to the number of hours. So you can just divide by 600. So you can just divide by 600 because every 600 minutes this number would increment from 0 to 1 and 1 to 2 and so on. So if these are equal, and also similarly what we want to do over here is this is empty by 10 mod 6. So basically this number over here, it increments every 10 minutes, and after every 60 minutes the next bit is incremented. So it goes back every 60 minutes. It goes back every 60 minutes and it increments every 10 minutes. So basically empty mod 10 shows that it's incrementing by every 10 minutes, but after 6 such increments we have to go back to 0. That is why I'm modding it by 6. This is how we will get the exact value at the tens place in the minutes column, and you have to equate that to the units place in the hours column. So this increments every 60 minutes, and every 10 hours the tens place of the hours digit will be incremented, and this will cycle back. So you have to do mod 10. So what I was basically trying to say is, let's say you are at 1 hour. So you will increment after 60 minutes, you will go to 2, then go to 3, then go to 4. Thus we are dividing by 60. But when you are at 9 and you add like 60 minutes more, you go to 0 again. So that's why I'm cycling back after every 10 steps. So that is why we are having divides and mods over here. I hope you understand. So now if these two are equal, then the number is a palindrome and we return true, otherwise we return false. And thus we count the total number of answers, which is answer. I hope that is clear. Okay, so let's move to problem E now. Okay, so in problem E, it's basically a problem of upper bounds and lower bounds. In this problem, we are given an array with lengths with zeros and ones, and in one operation, we can just remove either the first element of the array or the last element of the array. So in the end, what we will be having is we will just be, this is let's say our array, we will be removing prefixes of this array and we will be removing suffixes of this array and just keeping the middle array portion. And what we want is that the sum of this middle array portion is equal to s. So let's say our current sum is t. We want to remove the lowest number of elements such that we remove t minus s once from here. That is our goal. So one thing we could have tried is we could have just iterated through all of the prefixes and all of the suffixes. But for each prefix taking O of n time times each suffix taking O of n time, it would have been an O of n squared solution. But what we can do over here is an interesting idea. We can iterate over all of the prefixes as I said earlier, so that would take O of n time. But we could use some clever technique to find out the optimal suffix length in just log n time. That is how we get the solution down to O of n log n time. So that is the idea. So let's discuss our idea. So for that, let's discuss an example. Let's have our example was 0 1 1 0 1 0 1 0 0 0 0 0 1 1 1, something like this. So what we want is, let's say we want 3 ones. So if okay, 3 ones is too much. I'll just add up 1 1 here. Let's say we want 2 ones. If we choose the first one, we could have some set like this. We could also have some set like this. So what we want is, if we have 2 ones, we want to choose we want to take a particular one, and we want for the third one after that, we want to stop just before that. So let's say we have a 1 here. So this is the first one, second one, third one. So we want to keep as many elements in the final array as possible. So we just stop right before the third one. So for this we can use a function like upper bound. But on which array will be upper bound? So we need to find the prefix sums. So if we find the prefix sums for the given array, it comes out to be something like 1 2 2 3 3 4 4 4 4 4 4 5 6 7, something like this. Just a second. Yeah, everything's yeah, okay. So let's say we want s is equal to 2. We want 2 ones. So when we are at 1, let's say we are at 1, so we can only go till 2. That is because before 1 we had 0 ones, and now we want 2 ones. So our total number of ones should be 2. So what we want to do is choose the last index, largest such index, such that it has a prefix sum value of 2. So it is this index. And then, so this becomes our final array range. That means we have to remove all of these elements. This is how we are going to solve the problem. So what we want to do is, we want to choose a particular index. Let's say I will start at this particular index. I will start at 3. And I can only have 2 ones. So I can only go till 4. Like, because yeah, so what I mean is that till now, so if I start at this point, I check how many ones have already occurred. So those are the number of ones till this point. So those are 3 ones. So 3 ones have already occurred. We can have 2 more ones. So we can go till 5 ones. So essentially we can choose this entire array, because this array, before this array started 3 ones, we had 3 ones, and at the end of this array we have 5 ones. So only 2 ones are present inside this array. And what so basically, let's say we want to have we want to get the number 4. We can either choose this 4 or this 4, but it is always better to choose this 4. Let's say this was the set that we had, 2 to 4, and as compared to that, this was the set we had. This is a much larger set. That means it has much more elements in the final array, and thus we had to delete lesser elements. So we always want the last possible time we saw this number. So that is why we use upper bound. So we can deal with a few very simple cases first. So this is just a very simple way of calculating prefix sums. You just do from index 1 to n, a of I plus equals a of I minus 1. So normal array gets converted into a prefix sum. So what we want to do is, if the total prefix sum, the final index, tells you how many ones exist in the whole array. So if that is less than s, then there is no way we can have a sum of s deleting any elements. So just print minus 1. If it is equal to s, you need not delete any elements. So your answer is equal to 0 in this case. Okay. And yeah. Now we iterate over all of the prefix sums. For each index, we just so if so a of I minus 1 were the number of ones already before this particular index, and we want s more ones. So we want to find out the upper bound for s plus a of I minus 1. So from all of a, we find out the upper bound for s plus a of I minus 1. But it may cause some issue because when I is equal to 0, a of I minus 1 is undefined. So I use a ternary operator to check if I is not equal to 0. If I is equal to 0, you just don't add anything. If it is not equal to 0, you add a of I minus 1. This gives you the first index which is larger than your required number. So if you want 5, this is the index that gives you 6. So we subtracted from the beginning element to find out the actual index. So the like upper bound basically gives you an iterator. We subtracted from the begin iterator to find the index of this particular element. We find the index of this guy. Now, but we want to know the number of elements that we are deleting. So we are basically starting at I. So okay, let me just erase a few things. So we are starting at index I. So this was index I. We are starting here. We are going till just before index. So this is the index that we got, which I have mentioned as int in my variable. So we go till int minus 1. So number of elements that we keep are int minus 1 minus I plus 1, which is int minus I. So how many elements do we actually remove? We remove n minus n plus I elements. And if that, so this, okay, I'll write it here, n minus n plus I elements. So this is the number we actually want to minimize. So we just check if it is lesser than our current minimum. If it is yes, we update our minimum to get this new minimum. This is the solution to the problem. I hope it's clear. Now we move on to problem F. I think comparatively problem F was a simpler problem than problem E. Okay, so here we have an array and we have AI, AJ, AK. We want such that AI plus AJ plus AK, this sum should be divisible. Okay, on dividing it by 10, we should get remainder of 3. So one thing which makes the problem simpler is that we don't have to consider the tens place or the ones place for any of these numbers. We can just divide by 10 them by 10 and just consider the remainder and work with it. So what I do here is that I take my original array and then I find the then I divide them by 10 and find the modulo, find the remainder, and then create another vector b, so such that b of I represents the number of elements which give a remainder I after dividing by 10. Since we do not care about AI, we just care about AI mod 10. This is a very elegant way to represent it. Now what I want to do is that one interesting thing you can see is that you do not need to check for a lot of numbers. So divisible by 10, remainder 3, there are a lot of such numbers. There is 103, there is 213. You don't need to check them. Since we are just considering the units place, the sum can either be 3, 13 or 23. Since you are just adding 3 numbers which are less than 10, you cannot have any other number larger than this which has a units place of 3. So you just have to check whether the sum is equal to 3, sum is equal to 13, or sum is equal to 23, which you can do in a constant time. So if you can check 3 in, let's say, some x time, O of x time, so you can check 3, 13 and 23 in O of x time. So you don't have to spend another linear factor here. So how do you do that? So basically you just iterate over all of the possible i's and j's and k's that you have, since they can only go from 1 to 10, and you try to find out the sum of this I plus j plus k. If it is equal to 3 or 13 or 23, our answer is just yes. But we can't just say yes every time. So what we have to do is we go to b of I. If we have b of I, only then we continue. If there is no such number which gives a remainder I after dividing by 10, we just continue the loop. Similarly for j and similarly for k. And then we check if the sum is equal to 3 or 13 or 23, we select yes. If it happens nowhere, then we give an answer of no. Now there is an interesting problem here. Let's say I have a number called as 1001. So it will give me b of 1 is equal to 1. Now when I go through this loop, For I, this would work since b of I is equal to 1. J, it would work since b of I is equal to 1. And K, it would work since b of I is equal to 1. And 1 plus 1 plus 1 would sum up to 3, and this would give me an answer. But since we are only allowed for distinct indices, we cannot allow that. But we have already lost all of our indices. So what we can do here is that once we use up an element with remainder 1, we just decrement it. We just say that, okay, I no longer have one element, I just have 0 elements with remainder 1. So, and when I'm done with that loop, when I'm done considering that number, I will just give it back again. So here what I do is, once I use up 1 of b of I just subtract it by 1. Then I go to the next loop. Once I use up another b of j, I subtract it once again. But once this k loop is done, I have to try other j's with other k's. I have to try other pairs. That is why I just increment b of j again and increment b of I again. That is how we keep track that we are not using the same element multiple times. If we had to count the number of numbers, it would have been complicated since we are making some changes here and there, but we just have to say yes or no. That is why even if we get just one particular answer, our problem is done there itself. So this is how we are solving the problem. So this is the solution for F. So after F, we move on to problem G. Problem G was comparatively easier. I think it was simpler than E at least. Okay. So this is the relation that we have to satisfy. Once we understand the relation, once we see the relation, we understand the fact that you don't have to consider all of these elements. Like you don't have to consider 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power k. You can just consider simpler relations. You can just consider simply that a of 0 has to be less than 2 times a of 1. A of 1 has to be less than 2 times a of 2, and so on. So on. You can just consider this. So if this condition is satisfied, you can increment your subarray. If not, you can just stop the subarray at that point itself. So what I'm trying to say is that once I'm at the second element in my subarray, I don't need to check with a of 0. If I check with a of 1 and it is fine, and a of 1 is already fine with a of 0, you can already say that my subarray is of length 3. That is what we are trying to do over here. That is the whole plan. Okay. So we just start iterating through the array whenever we find a good pair, so that this I satisfies the condition with I minus 1. I just increase the size of my good pair, and whenever it doesn't, then we have to stop our current subarray, because this subarray cannot be used. Like subarray containing I and I plus 1 cannot be used, so we will stop there and there itself. So what I'm planning to do is that, let's say I have something like a of 0, a of 1, a of 2, a of 3, and a of 4. Let's say a of 0, a of 1, a of 2 satisfy the condition, and a of 3, a of 4 satisfy the condition, and k is equal to 2. So what I do is, I get till point a of 1, and say, okay, till now the condition is being satisfied since a of 0. And I just check what is the length now. So length is 2, and the condition since which the length is being satisfied is 2, which is greater than or equal to k. That is why I increment my answer by 1. I come here also the condition is satisfied. Now the length of the sequence is 3, but my k is still 2, which is still lesser than size. So here also I add 1 to the answer. When I come at this point, I find that the condition is no longer being satisfied. That is why my new subarray size which satisfies the condition is just 1, which is just this element itself. Since one element will always satisfy this condition, but 1 is lesser than 2, hence I do not add anything here. But again, when I go to a of 4, I understand that my sizes become 2 again, which is equal to the value of k. Thus I can increment my answer by 1 more. Thus my total answer is 3. This is the exact procedure that I am using. So my initial size is 1. I iterate through the array from left to right. I see if the condition is being satisfied at a particular point, I increase the size. Otherwise, I just set the size equal to 1. So for example, if this guy doesn't satisfy the condition from before, he will start the new chain. He will start the new chain from which the condition is being satisfied. And if the size at any point is greater than k, we can choose the last 2 elements. For example, here the size was 3 and k was 2. So I just chose these last 2 elements as a valid subarray. So if at any point if size is greater than, so if size is greater than k, you can just increment 1 to the answer and then just print the final answer. So this was the solution for problem G. I hope the solutions were fine and useful. Thank you.